and promising branch of robotics. It is a new branch of robotics that has been drastically dominated over the science through mimicking of living things through soft material to exactly copying them from physical and functional scenarios. Soft robot perform way better in particular areas like biomedical, prosthetic robotic arms, and manipulator etc. The motion of soft animal can't be achieved through conventional robotics or rigid robots like the way an octopus moves, swim, or crawl, for mimicking these species motion and deformation that a conventional robot can't. Underwater exploration is one of the areas of soft robotic. The idea to mimic soft creature can be very beneficial for underwater creature. We have designed and simulation on SolidWorks under fluidic environment and having SMA actuation, where we loaded all the fluids. The simulation study mainly found the displacement, the stress, and the strain of the tentacles. Also, a mathematical modeling of our octopus model have been driven. An octopus model is designed using mold casting techniques and SMA actuation.
Simulation modeling solves the real-world problems very efficiently and very easily. It provides very useful methods of analysis which are easily understood, which are easily communicated and easily implemented. Moreover, simulation studies provides a very useful insights into the complex systems, which helps us to understand these systems much better than without the use of simulation studies. So going with the wind and recognizing the importance and wide adaptability of the simulation studies, we also have used the simulation study in our project. So the software that we have decided to choose is SolidWorks. SolidWorks we have used for two purposes. The first one is the 3D designing modeling of the octopus modes and overall octopus model, and second is the simulation study. So the simulation study is carried out in two categories. In the first category, we have simulated the shape memory alloy wire, and we had two types of shape memory alloy wires with a different dia. The first one was a 0.3 mm shape memory wire, and second one was 0.5 mm shape memory wires. So the environment of SolidWorks simulation that we have said is that we actually have made use of the finite element method and the SolidWorks flow simulation, because the ultimate target of our final product or end product of our project, that is a bio-inspired soft octopus robot, is to swim in underwater applications. So in order to calculate all the fluid loads and the gravity effects and all the pressures that are incorporated on the tentacles of the octopus, on the head of the octopus, in order to consider that, we have made use of the SolidWorks flow simulation. And the fluid that we have used is water, and the temperature we have for that, the temperature conditions are the standard temperature conditions, which is 25 degrees centigrade. Moreover, the reason behind choosing this standard temperature conditions is that this shape memory alloy wire that we have simulated is very responsive to the temperature variations, and this also serves the basis for its working. So first of all, we have simulated the 0.3 mm wire in the SolidWorks flow simulation, and then after we have exported the results into the finite element method, and we have applied the temperature loads at different temperature ranges, and the results of strain produced in the shape memory wire and the displacement produced in the shape memory wires are calculated and plotted accordingly. Same goes for the 0.5 mm shape memory wire as well. We have adopted the same strategy. But when it comes to the overall model of the soft octopus robot, we actually have used the EcoFlex 0030 material. So to perfectly to most nearly mimic the soft octopus in the simulation environment, we have made use of these two materials. We have made the tentacles of the material from the EcoFlex 0030 and the head as well. But another thing we have done is that we have embedded the shape memory alloy wires of 0.5 mm dia into the tentacles of the soft octopus robot. So The second thing is that is already described about this shape memory alloy wires. Going with the same procedure, we also have conducted first of all the SolidWorks flow simulation for Octopus tentacles and Octopus model as well. So in the flow simulation, we have kept the parameters same that we did for the shape memory alloy wires. So after calculating the forces like drag and other fluid forces, we have exported the SolidWorks flow effects to the SolidWorks finite element simulation environment. So where the temperature to the tentacles is applied and all the fluid loads are removed, are actually implemented to mimic or to plot or to gain the results which are as nearly equal or nearly mimicking the original results in the physical environment. And moreover, the graphs, the results that we have generated are for the strain, for the displacement, for the stress and the force or the thrust force generated by the Octopus tentacles as well. So this is all we have done in the simulation part of the project, and we are very glad to say that we have successfully conducted it, but there were some issues, some challenges we faced because of using SolidWorks. Because of the many advantages of the SolidWorks, it also lacks in some aspects. Very phenomenal or very important aspects I would like to mention is that SolidWorks lacks moving mesh, which limits its ability to really simulate any Octopus model or any kind of model that displaces from its original position to different position. So that is why we have adopted a different approach, because SolidWorks provides a very versatile options. So we have first of all gone for the SolidWorks flow simulation, then we have exported the results to the finite element method, and we have successfully conducted one method. And these results are perfectly, or not perfectly, but in near approximation matched to the what we have done physical. Thank you very much.
As the mathematical model is concerned, we have implemented in model the SMA wire and the SMA wire and the Octopus limb force, Octopus limb force generated. So let us talk about the force generated by the limb. Basically, we have divided the limb into two parts: the proximal part and the distal part. The proximal part is attached with the body of the octopus, and distal part is away, we can say is second part of the limb, and the distal part is restricted with the limb force or limb movement. Now this is very common. If I say the limb is, if the limb is moving downward, definitely its cross section area will decrease. So this is how we model this theoretical concept in mathematically. So this is our mathematical model for generated muscles force. Fm is equal to Fi A of D into divided by A of I. So Fm is the net force or internal force generated by the octopus arm, and Fi is the initial force generated by the octopus, and A is the area at a specific position, and A of I is the area at starting position. There is one factor that will affect the octopus limbs force. This is drag force. So the drag force is separated from the muscle force, because it will provide resistance. So this is how we computed the force, and the drag force is always general, because it's always depends upon the shape, how the geometry of the object is. And then for the octopus, we have calculated the dimensionless drag force CD. We have calculated CD, and the mass density, how the mass density is calculated, P is equal to 0 to L into rho s into ds. So the L is the length of the octopus limb, So from the proximal part to the distal part, we have calculated the momentum of the arm. So this is calculated. Now this is very important thing. If S is less than D, like if S is a proximal part, the force, the velocity of the arm will be 0, and if S is greater than or equal to D, like if S is the position of the S is the position in the distal part, the force, the velocity will be 2D. Now we have assumed if S is less than D, the proximal part is at rest, no movement. So we will just calculate the distal part movement. So part movement is calculated using the formula F is equal to d over dt, because we are just talking about the small part of the ds. So for the whole limb, from the starting position to the whole distal part, the length is 0 to d and d to l. So the first one will always be 0 to d, because we can see the proximal part will not move, so the force there will be 0. Where m of d is the mass of the distal part, so the mass of the distal part is taken as, and then using the equation we have just using the above equation we just put the values of m, and the acceleration is already given because we have used Newton's second law. So the force is calculated like this. Now we have just calculated the m of d, and m of d was just a single part, was a fraction. We have to have the mass for the whole distal part of the limb. So after integration of this, we have put the value in the equation, in the first equation, in the above in the E. This is the force generated by the octopus limb reaching towards an object. So 2a m of d minus 6 into m of t upon l 1 minus d upon l whole square into v square. So the second mathematical model is modeled, the development of the model for SMA wire. This is the property of the SMA wire. When we provide the temperature, it will secuse, and if the temperature is lower, if we put the SMA wire at low temperature, the SMA wire length will expand. So using this information, we have graphed the SMA wire property. So what if I talk about the diagonal? If I draw a diagonal from the end point, so this would be a linear equation. So the linear equation is plotted there. Just like we can see, it is a lower and upper part for the cooling and heating. We have drawn a straight line from the end of the hysteresis loop. This would be a linear equation. So the linear equation always needs a slope. So we calculated the slope. Y of 2 is the length and y of 1 is also the length, and the denominator shows the temperature from T2 to T1. So using the distance formula, we have calculated the distance between the endpoints of the hysteresis loop. The two sides are shown above. So then we have just assumed that this would be a sinusoidal curve. So using sinusoidal equation, we have implemented the SMA wire mathematical.
For hardware, the biomimetic soft octopus robot is made of soft material which works as a matrix for shape memory alloy wire. The robot contains head and the tentacles. All 8 tentacles are identical to each other. Moreover, the limbs are made of soft and elastic material named EcoFlex 0030. The actuation mechanism of the soft octopus robot is based on the thermal simulation of the shape memory alloy wires. When the voltage is applied to shape memory wire embedded inside the tentacles, current starts flowing, causing heat that ultimately results in shrinking of shape memory alloy wires, leading to the movement of the octopus tentacles. This movement, when repeated, generates locomotion. Simply, the shape memory wire contracts on heating and expands otherwise. Each of the 8 arms of the octopus contain the SMA embedded in the soft material. Using this phenomena of the SMA wire, the 8 arms of the octopus contracts when the voltage is applied and it expands when the voltage is removed. In addition, SolidWorks is the software also used for designing the die for the molding of the soft body. Moreover, the die is designed separately for the octopus head and separately for the octopus tentacles. For the model, all the 8 tentacles are produced using only one mold. That mold is designed in SolidWorks environments. It is actually molding and casting techniques to cast the soft robot. Using the molds. The hard molds are designed in SolidWorks and later they are 3D printed using 3D printer. So the trained shape memory alloy wire is inserted when the material poured in tentacles mold was half cured. Each tentacle is further then divided into 2 parts as upper part and the lower part. These both parts are then tightened using the nuts and bolts in order to avoid any kind of liquid leakage that has been poured inside the molds. The purpose behind creating the split head or split tentacles is to remove the casted material at a half cured stage from the die, because at this stage tentacles or head are to be attached. Tentacles are to be attached with the head of octopus, offering greater flexibility in terms of handling. There are 8 spaces left in the bottom of the head for attaching the 8 tentacles. The design of the tentacles is simple and it is bent with hollow space left inside. The diameter void space for the tentacle is 7 mm and the length of the void space is 79.12 mm, whereas the overall length of the tentacle is said to be 93.51 mm. Similarly, as the tentacles is divided into 2 parts as upper and lower, the head is also made with 2 parts and they are then tightened together using the board. Similarly, EcoFlex 0030 is the material used for the head of the robot. Moreover, for the head we had only one piece of the mold and it was all required. The same material EcoFlex 0030 is used for manufacturing the head of the octopus. It can be seen that there are grooves made on the mold for the head of octopus. These grooves are there to attach the tentacles. So the material was prepared and poured in the mold. It was placed inside a temperature control box at almost 60 degrees for 6 hours. The cured head was then carefully peeled out of the mold. Now the head and the tentacles are manufactured. The next step is to combine both the head and tentacles of the octopus. The idea is to attach the tentacles in the head when the head is half cured and it is inside the mold. Thus, after almost 2 hours, the material became half cured and then the tentacles are attached. As a result, the tentacles are fused in the head and look like a permanent fixture. Now this is the complete octopus prototype that we have prepared. In addition, the complete working of the octopus hardware model is depicted in this following figure. It shows the circuit design along with the pulses generated by the Arduino Nano controller. Additionally, the flow diagram shows the complete process including the hardware and software interactions and complete working process for our octopus robot.